Welcome, ladies and gents, to this lecture on wave phenomena. First, I'd like to talk about reflection. This is a term that you've probably heard of before. However, its context is often just related to a visual reflection. For example, you've all looked in a mirror before, and you've observed your own reflection. What are you truthfully observing? Well, light is an electromagnetic wave, and as that light strikes a mirror, you observe that light bouncing back and reaching your eye. So essentially, a reflection is whenever a wave strikes some boundary between two media, meaning two different substances, and bounces back into the substance that it was originally in. So light traveling through the air strikes a mirror and bounces back into the air, and that is the reflection that you observe. Another example of this would be something like an echo. An echo, in terms of sound, is created when you send a sound wave at a barrier and you bounce back and you listen to its reflection. That echo is simply that sound wave coming back into its original media, meaning the air, after hitting off of something else like a barrier, whether it be a wall or a rock or some sort of hard surface. Now, there are two different types of reflection, and they are called open and fixed end reflection. Open end reflection is when you have a wave that travels from a more rigid medium and reflects off of a less rigid medium. As a result, you get this, let's say a wave crest if it's going in, to come back in its same exact orientation or as a crest as it comes back into its original medium after striking, let's say, this boundary. The opposite would be a fixed end reflection, and that's when you go from a less rigid medium to a more rigid medium. And as a result, you get an inverted wave, or let's say you send in a crest from your original medium. When you strike the boundary, you're going to get a reflection as a trough, or an inverted wave. Now, often reflection doesn't occur without also having this other process occur that is called refraction. Refraction is when a wave is transmitted from one medium into the next. So essentially, as a wave strikes a barrier between two media, what often happens is part of the wave is reflected, meaning some of that energy is taken and bounced back into its original medium, and then the remainder of that energy is actually refracted or transmitted through the first medium into the second. Now, as this refraction or as this transmission occurs, waves can actually change their speed and wavelength. This doesn't always necessarily occur if the substances are very similar. However, most of the time when a wave travels from one medium to the next, its wavelength and speed changes. However, its frequency will always remain the same, or how often it occurs. Now, sometimes also when you strike a medium at an angle, what will happen is the wave itself will actually bend as it goes from one medium to the next. This is caused by the change in speed of the wave. Now, in this case of refraction, where a bending occurs, what's happening is part of the wave is getting through before, like let's say the upper half of the wave is getting through before the lower half of the wave, so it causes the wave to actually turn. An example of this would be if you put a straw or a spoon in a glass of water. If it strikes that water at an angle and you look at the boundary directly between those two media at that angle, you'll notice that it appears as though that straw or spoon is kind of disjointed or broken. And this happens because you're observing the light as it bends from air into water. Next up, we have diffraction. Diffraction is a wave property that describes the bending of a wave around a barrier. This can be easily observed with light and sound. If you've ever turned off all of the lights in your house, but still had, let's say, light coming in from one source, or let's say from outside, what you'll notice is sometimes the light will actually bend underneath a doorway or around a window entrance, in that it actually strikes or hits some of the objects that aren't in direct line of sight of that light source. What this is that's light diffracting or bending around a barrier. Another example of this would be with sound, in that you can often hear sources of sound that you can't directly see. And that's because the sound waves themselves will bend around any obstacles or barriers in your path that prevent you from observing or seeing that source of the sound. Lastly here we have superposition, and that's when waves pass through the same region within a medium and they actually interfere with one another. Sometimes they will interfere constructively, in which they build each other up or add an amplitude, and other times they will interfere destructively, in which case they have opposite orientations and they cancel each other out or subtract an amplitude. Two different examples of this would be, let's start with destructive interference. If you have something called noise-canceling headphones, what they do is they essentially take the ambient sound in a room, invert it, and send it back in through your ear. As a result, you hear both the inverted wave and the actual sound wave at the same time, which causes a destructive interference such that you don't hear any of the ambient sounds within your room. An example of a constructive interference would be if you have multiple instruments of the same type playing in an orchestra or a band. Often they have the same exact part because what you're looking for is an increase in the amplitude of the sound. So if you have several trumpet players playing the same note, they produce a louder version of that note. This can be often useful in a band because you want to hear a loud sound for a specific part. As a result, you can increase the amplitude by just playing that same note or that same source over and over and over again through the same region. When we apply some of those wave phenomena, or those wave properties, we can often get some interesting effects. One of these is what we call a standing wave. This is created through two processes, and that is reflection and interference. A standing wave is a wave pattern of wave crests and troughs that remain stationary in a medium while the wave reflects and interferes with itself. If you look at my diagram here, I know it's a little sloppy. Essentially what I have is I have our initial waveform, which is this black line here that goes up and down. And you can see the crests and troughs as it goes along this equilibrium line that I have placed here, this purple line. As this wave goes along and it hits the end here, it actually reflects backwards, and that's what you see the little orange dashed line here. And essentially this is what we would call a standing wave diagram, where you have the initial waveform and then its reflection coming back through. Now, there are two very important vocabulary words that go along with standing waves. The first one is what we call a node. That is an area of destructive interference. It's where a crest and a trough would meet, and the resulting wave is just simply a cancellation. Whereas when you have a crest and a crest or a trough and a trough, you create what we call an antinode. And that's what we would consider these like loop-like shapes. And what they are areas of constructive interference. So an example of an antinode would be the circled in green area here, where you have both a trough and a crest kind of drawn. That loop is just showing that you either have a constructive interference or a destructive interference with your reflection, and it's happening over and over and over again. Standing waves happen whenever you fix a wave's reflection between two rigid boundaries. And we can often create these through just using waves on a spring and just having someone move the spring up and down. But standing waves, these patterns can also be created through sound waves often. When you fix a sound wave between an area in which it will echo or reflect backwards, you will produce this standing wave form. The last part of my lecture here is actually something a little bit off topic, but it's to talk about another important aspect of describing waves, and that's what we call phase. You might have heard this term before, but the phase of a wave essentially refers to its orientation, or its position or the position of a certain point in time on a wave cycle. Now, I drew a wave cycle here and labeled each of the phases on this wave corresponding to the different points on this wave. So phase is essentially just a way to describe the position of where you are on a wave. So point A here, I said was 0 degrees because it's at its starting position. Now, if you remember about sine and cosine curves from maybe some of the trigonometry that you've learned, Technically, a full sine curve is when it goes through 360 degrees, or 2 pi radians, as you may have heard it described. Now, this is one full cycle of a wave. Now, at 360 degrees is where, if I were to keep drawing this curve, it would basically start over again. It would look like just like what we see at A. Now, 0 degrees is where we start. 360 degrees is where the next cycle of the wave starts. So if I want to describe any of the positions in between, I can break it down easily into quarters. Meaning from A to B is 90 degrees, or 1/4 of the wave. From A to C is 180 degrees, or 1/2 of the wave. This is how we can describe the phase difference, or the phase shift on a wave, or any 2 points on a wave, rather. 2 points on a wave are said to be in phase if they're at the same exact position relative to the wave's cycle. An example of this would be points A and E, because even though they're at different locations, they're relative to one another. If we were to describe what would happen at E, this would be the start of a wave again, the start of the cycle. Likewise, point A at 0 degrees was also the start of the wave, or the start of the cycle. Out of phase refers to different positions relative to the wave. Now, often we describe this in terms of an angle, or what we call a phase shift. For example, if I want to get from A to B, I have to travel 90 degrees on my wave. So they are a phase shift of 90 degrees. Similarly, from B to C is a shift of 90 degrees. So if we were to consider points B and C to be out of phase, by how much would they be out of phase? Well, 90 degrees, because they are 90 degrees apart. Let's look at a different example. If you look from C to E, that's 180 degrees to 360 degrees. They would undergo a phase shift of 180 degrees. That's the same exact phase shift between points A and C. So just to point out another example here, if I wanted to have a phase shift of, let's say, 270 degrees, that would be like going from point A to point D. And another example of that could be from point B to point E, because once again, those 2 points would be 270 degrees apart from one another. Realize that when describing a phase shift, it's all relative. You need 2 points to compare to describe the difference in phase amongst a wave. All right, ladies and gents, that concludes our lecture on wave phenomena.